Right, so let's look at the idea of serial dilutions. And I mean, the word serial means you start with one thing, then you do something to it, and then you continue on with that thing that you've newly created, and you continue on with it, and you continue, and you continue, and you continue. So it links to exactly this. Serial dilutions mean you have a solution of specific concentration, and then you do something with that solution. You take a part of it, you put it into a new flask, and then you make it more concentrated or less concentrated. Well, less concentrated because it's a dilution. So you dilute that solution. Then you take the dilute solution, you take a small bit of it, and again, you put it in a new flask and you make it even more dilute. So that's the idea here. So let's read the question. It says, consider 750 milliliter of a stock solution. So stock solution just means something that has been made up and we know exactly its concentration. So we know the concentration of this solution is 1 molar copper nitrate. Then two dilutions are made up as follows. So you need to read them in sequence. A 50 milliliter of the stock solution is pipetted into 250 milliliter volume flask and made up to the mark with distilled water. So in other words, it means in our first step, we will take some of the stock solution, a bit of it, put it in a new flask, and add enough water to make up a 250 milliliter solution. Then in B, it says 10 milliliter of this new solution, this new one that we made up. So this actually refers to small a, is pipetted into 200 milliliter volumetric flask and made up to the mark with distilled water. In other words, again, we add enough water. But you see, each time we take a small volume of the previous solution and we add more water to that bit of the solution. In other words, the concentration of the species will change. Right. We're told then to determine the concentration of nitrate in solution B. So let's start with the qualitative diagram. So volumetric flask is a thing that looks something like that. We start with one that is 750 milliliter, so made up to its mark, and we're given a concentration of not N, of copper nitrate equal to 1.00 molar. Right, that's what we start with. We have 750 milliliter of that thing, and we have a concentration of as such. In our next step, we're then told we only take 50 milliliter of this solution and we put it in a new volumetric flask. In a new volumetric flask, this volumetric flask has a total volume of 250 milliliter, and we put in first, if you want to think of it visually, we add the 50 milliliter, so there's the 50 milliliter, and then we add enough water. So then we add water all the way until we get to that point. So now the question is in this first step, what happened to the concentration of our copper nitrate? How would we determine what the concentration is of the copper nitrate in this solution? So we first start the conversation there. Will it be the same as the stock solution? No, right? So we took a bit of the stock solution, so a certain number of mole of copper nitrate was taken, placed into a thing, and then more water was added until a certain volume of solution was made up. So the bigger question here is, what is the number of moles transferred? So what is the number of mole of copper nitrate transferred? Because to calculate the concentration of the copper nitrate, we will take the number of moles of copper nitrate present in this solution divided by the volume of the solution, right? And why is this important? Is the number of moles that we had in the stock solution the same number of moles that we transferred to the new solution? No, of course not, because we only take 50 milliliter of something that definitely has a concentration that is the same, but the number of moles will be different. So because we only take 50 milliliter of a 1 molar solution, that implies we take a certain number of moles. And you need to think of the new solution as you place a certain number of moles of something in 250 milliliter of solution. So that means you'll get a new concentration. So let's apply the same logic to the next step. The next step says 10 milliliter of solution A. So again, we say take, so this one is name is A, right? Take 10 milliliter of A, and we put this into a 200 milliliter volumetric flask. So this one's line is there, 200 milliliter volumetric flask. And again, the same idea. So only a little bit of the solution is here. This is solution A. And then we fill it up to the mark with water. So again, what is how will we calculate the concentration of the copper nitrate in this? 3, 2. We would need the number of mole of copper nitrate divided by the volume of the solution. And each of these cases, the volume of the solution is the new volume in the volumetric flask that we make up. Question is, what is the number of mole of copper nitrate transferred? Right, so you can see what we need to calculate every time. We need to determine how many moles is transferred to the new beaker or the new flask, then we determine its concentration. Then we take some of that new concentration stuff, we put it into something else. So again, we need to determine how many moles is actually transferred, and then we can calculate the final concentration here of our solution B. Okay, so let's start with that. How do we know what the number of moles of whatever is transferred in the first case? So how can we calculate NCU NO3 2? Well, it's going to be equal to the volume times the concentration. So we'll take 1.00 mole per liter, multiply that with 50 milliliters, in other words, 50 times 10 to the negative 3 liter. I think there's a specific number of significant, 2, so it's 50.00 times 10 to the negative 3 liter. In other words, you will get 50 times 10 to the negative 3, which is 0.05, and then there's a bunch of zeros, so there's 3 significant figures, so it's 1, 2, 3 molar. But actually this is an in-between step, so you don't have to worry about the significant figure. So you know this to a certain extent, but you know it's 0.05 molar. Right, so that is, not molar, it's the number of mole, apologies. So many mole in our new solution. And what is our new solution? Our new solution is this situation right here. So the concentration of copper nitrate in A must be equal to the number of moles of copper nitrate that we transferred. So let's give it a name. We call it A as well. So we just put a little A here. divided by the volume. And what is the volume of the solution? The volume of the solution is this 250 milliliters. So again, it's divided by 250. But first, let's write out the stuff. There's the volume of the solution A. So that then gives us 0.0500 mole divided by volume of the solution is 250 milliliter. Now it's 250 times 10 to the negative 3 liter. You can take the 10 to the negative 3 up there, so then it's 50 divided by 250, which is 1 over 5, so it's 0.2, 0.2000 molar, because it would be mole per liter. Right, so that is the concentration of copper nitrate in solution A. What do we do? What do we do then? Then we're told we take 10 milliliter of this new concentration and we add it in a 200 milliliter beaker, and we make up that 200 milliliter beaker to a point of 200 moles. So what we do again is we first calculate the number of moles transferred. So the number of mole of copper nitrate in B, so transferred to B, would be the concentration of copper nitrate in A, not equal, multiplied by the volume taken. And in this case, so this is 0.2000 molar or mole per liter, and this is 10 milliliters, so 10.00 times 10 to the negative 3 liter. So again, negative 3 times 10, so it means it's 1, 2, so it's 0.01. So this just becomes 0.02000 and onwards, mole, not molar, mole. Importantly, so you notice that the number of moles that we transferred is, we started out with a larger number, so 0.05, and we now have a smaller number. And why is that? Because every time we've diluted the solution, we've only taken a certain percentage of the total number of moles to the new thing. We've made up a concentration. Then we take a specific percentage of those number of moles again to the new thing, and we made up a new concentration. So you should see that. If you don't see that trend, then you're doing something wrong. Okay. And then we have the number of moles. In other words, we can calculate the new concentration of our thing. So concentration of copper nitrate in B is then equal to the number of moles. So the number of moles of copper nitrate that we've transferred to B divided by the volume of the solution. And in this case, those values are 0.0200 mole divided by the volume of the solution, which is 200 milliliter. So we look at what the thing is that we make up. We want 200 milliliter. So that is 200 times 10 to the negative 3 liter. Of course, we want mole per liter. We want molar. Again, 10 to the negative 3 upstairs becomes 1, 2, it's 20 over 200, which gives us 1 over 10. So it gives us 0. Is it that? 20, 1 over 10? Yeah. Gives us 0.1 molar. Right. So I mean, that is quite straightforward in principle to do. Maybe just check my calculations. I did this all in my head. So there might be a little bit of a mistake up to this point, but we're not done yet. What is the concentration of nitrate was the question, right? We were asked, determine the concentration of nitrate in solution B. And what did we calculate here? We calculated the concentration of copper nitrate. And what is the relationship in copper nitrate, or copper nitrate for between copper and nitrate? So the basic question, or the question I'm actually asking here, is if you have copper nitrate, how many copper ions would you get from the solution of copper nitrate? You would only get Cu2 plus. And nitrate ions, you should get 2 NO3 minus. Hence, the concentration of NO3 minus, so what we want to write here, what we were asked eventually, NO3 minus is equal to twice that of the copper nitrate, and that will be equal to 0.2 molar. Okay. You can logically argue this situation out for yourself. In principle, so let's say, for example, you had a chemical reaction where you had copper nitrate 2, and that just needs to split. So what do you get? You get copper 2 plus 2 NO3 minus. And if we have 1 copper nitrate, we'll form 1 copper 2 plus, and we'll form 2 mole of NO3. So hence, if we want to calculate the concentration of copper 2 plus, and we have to calculate the concentration of NO3 minus, we would say the concentration of Cu2 plus would be equal to the number of mole divided by the volume of the solution. And this one would also be the number of mole divided by the volume of the solution. But how do we relate it? So we have the number of mole of copper nitrate. So this one will be equal to the number of mole of copper nitrate divided by the volume. And this one will be equal to twice the number of mole of copper nitrate. So it will be twice the number of mole of copper nitrate, which will be a 2, divided by the same volume. And hence, then you can write this one as 2 times in copper nitrate divided by V. And of course, then relate those terms. So you see this term popping up here. And what is in front of it? A 2. So that's why it's twice. The nitrate is twice that the concentration of the copper nitrate. And of course, because NCONO/V is otherwise known as the concentration of copper nitrate. Keep on worrying whether or not this answer is right. It might be 0.02. So maybe just put it in brackets. If you get 0.02 molar, it might also be correct. I might have missed a factor of 10 somewhere. I mean, it happens. I mean, I'm also human. So, yeah, but 2 over 20 is, yeah, anyway. All right, so at least if you follow the logic, then you should be fine up until the point. And again, of course, if you're asked in the question, then you need to write out the logic. So you must say, the number of moles transferred from the stock solution to solution A is this. Hence, the concentration of copper nitrate in solution A is calculated by this. Next, only 10 milliliter of solution A is taken, hence the total number of, or the number of moles of solution, or the number of moles of copper nitrate in solution B is this. Therefore, the concentration is now this. However, there are 2 nitrate anions for every 1 copper nitrate molecule that is dissolved. Therefore, the concentration of NO3 is twice that of the copper nitrate. Okay, and that's the proper way to write it. You don't actually just do calculations. General thing that also will be asked is, why don't I use C1 V1 equals to C2 V2? The answer is because you have no idea what that means. So what is the C1? What is the C2? What is the V1? What is the V2? So yeah, you have the C1, that's the stock solution. You have the volume of the stock solution taken, that's 50. And you have the volume of the next solution, 250 mol. So then you can calculate C2. From that, then you have the concentration and the volume of the next one, and you have the volume of the next one, you want the concentration. So yeah, you can do that. You can go check that it technically works out exactly that what I did. But this is the logical, better way to do it than just plugging in equations like someone who doesn't know what they're doing. Okay, so, but I mean, it's a free world. You can do what you want. All right. I hope this assists you in your study. And I wish you all the best of luck with your endeavors in life. All right, so I'll see you in the next video. Thank you for watching. Actually, just figured out what the problem was. Here, the answer should be 0.002 mole. And then, of course, everything moves with a factor of 1, of 10. So then that becomes 0, and that also gets 0.02 molar. All right, so figured it out 2 seconds after I stopped the video. All right, thank you for watching.